All right, we are in the second of two sections of discrete mathematics. We've talked about number theory. Now we're going to move on to graph theory. Not graphing as in graphing functions, but more like vertices joined by edges. So kind of a geometric graphing section of this option. So first we've got to get some terminology straight. I am going to go through this once, but once I do that, you're expected to know what all the terms mean. So let's talk about them one by one. First of all, any graph is just vertices and edges. Not all of the vertices need to be joined by an edge, but it's just a set of vertices and edges. A simple graph would be any graph where any two vertices are joined by an edge. Okay, at most one edge. So they might be joined, they might not. But if they're joined, they're only joined by one edge. And so the opposite of that would be a multigraph where you might have a loop that starts and ends at the same vertex. Or you might have two vertices that are joined by more than one edge. So that's a multigraph. If we're talking about the degree of a vertex, that just means the number of edges that touch that vertex. And a loop is kind of a tricky situation because it does start and end at that vertex. So I believe whenever you have a loop that you count the start and the end of that edge as two separate edges. But we'll see in examples how that's handled. Adjacent vertices are just vertices that are joined together by at least one edge. It doesn't have to be exactly one, it could be more. And an incident edge is any edge that ends at a given vertex. So you can say that an edge is incident with a vertex if they are connected. The order of a graph is the number of vertices, and don't get that confused with the size of a graph, which is the number of edges. So two different measures of a graph. Okay, and we've talked about what a loop is. That's just an edge that starts and ends at the same vertex. All right, and then we've got more here. Let me just hide some of this so that it's not too much information all at once. Any connected graph just means that you can get from any one of the vertices to any other vertex. So that that it's not two separate graphs. You can't separate the graphs into two distinct graphs. It's basically possible to get from any vertex to any other vertex using the edges that are there. A complete graph means that every possible pair of vertices you can connect are connected by one edge. So that would be complete. So no edges are left out. A circuit graph is just that. The edges form basically the perimeter of a shape, and none of the diagonals of that shape are included. Then you have a wheel graph. That's the perimeter plus one vertex inside that circuit, and all of the vertices on the outside are connected to that vertex on the inside. We can also talk about a subgraph, which is basically any graph that is made up of a subset of the vertices and or edges of that graph. We can talk about a regular graph. Remember, regular polygons were those polygons where every side was the same length, every angle was the same measure. With a graph, every vertex has the same degree. Okay, so it has the same number of edges leaving it. Okay, complement, that's like complementary angles. Whatever you would have to add to make 90, that's a complementary angle. Well, whatever you would have to add to a graph to make it complete, that would be the complement. So it's the same vertices that are there, but any edges that are there are not there in the complement, and any edges that aren't there are added to make the complement. So that is the complement. A planar graph, that relates to the word plane. Basically, if you can take a graph that is three-dimensional and you can draw it in such a way that it's two-dimensional and none of the edges cross, that's called a planar graph, and we get into more detail with that in a later section. Bipartite means that the vertices can be separated into two sets, and each vertex from the first set is joined to a vertex in the other set, but the vertices within each set are not joined to each other. Okay, so that's kind of like x's being joined to y's, but you would never join x's to x's or y's to y's. Okay? And then there's something we call the adjacency matrix. That is a matrix, it's a square matrix, and basically you label each column and each row with a vertex name, and if those vertices are joined by an edge, you put a 1 there, or how many edges there are joining those two vertices, And if they're not connected, if those two vertices are not connected, then you just put a 0 there. So that's an adjacency matrix. And it is symmetric about the diagonal of that matrix, but we'll look at an example of that. Isomorphic graphs, written using the same symbol for congruent when you were in geometry, but basically they're the same graph. Everything that was connected in the first one is connected in the second one, but it just looks a little different. Maybe the vertices are named different, but the connections are the same. All right, so those are isomorphic graphs. So let's look at this example here. I've got 4 vertices, A, B, C, and D. I've got 5 edges, and so the order is 4, and the size is 5. It's simple. There are no loops. There are no edges, or sorry, there are no pairs of vertices that are joined by more than one edge. It's connected. You can get from any vertex to any other vertex by following either an edge or a series of edges. It's planar because none of the edges cross each other. If I look at vertex A and vertex C, those both have degree 3. And if I look at vertex B and D, those both have degree 2 because there are 2 edges that are incident with those vertices. All right. Now, if I keep talking about that graph, let me scroll down a little bit. Here's the adjacency matrix. And basically it's saying that A is not connected to itself, but it is connected to B, C, and D by one edge each. B is connected to A and C, but it's not connected to B, or it's not connected to itself, and it's not connected to D. C is connected to A, B, and D, but not itself. And D is connected to A and C, but not B and not itself. Okay, and I can draw an isomorphism using vertices E, F, and G, and H. And you can see it's basically the same structure. If I fold F up like this, it's going to look almost exactly the same, but maybe rotated. And then the complement of it, B and D were the only vertices, I guess, that weren't connected to each other. So that's what the complement would look like. That's the only edge that's missing that would have made it complete. All right. And so now here's some results. We talk about the handshaking lemma, which basically means the sum of the degrees of the vertices is twice the size of G. And as a result of this, any graph has an even number of edges of odd degree, and these are known as odd vertices. So just a couple of results that we will discuss further in class. If you have any questions, please let me know, and I will see you tomorrow.